This video will discuss taking repeated derivatives for partial derivatives. So for f of x, we define the second derivative with respect to x as the derivative of the derivative, or the derivative of f prime or f double prime. So if we have f, which is a function of multiple variables, let's say x, y, z, for example, the second partial derivative of f with respect to x is going to be the partial derivative of the partial derivative with respect to x. We're going to apply the partial derivative rules twice. So that was a fairly cut and dry case for single dimensional functions, because that's all there was. You take the derivative rules as many times as you need to. There's one extra caveat here in multiple dimensions, is that we can have something called a mixed partial derivative. In this case, a mixed second partial derivative. So d squared f dx dy is where we take the partial derivative with respect to x of the partial derivative with respect to y. So these operators, just like most operators, work from right to left. So first we take the derivative with respect to y of our function, then we take the derivative with respect to x. And there's a very nice property which is going to come in handy in thermodynamics for what are called Maxwell Relations, which is the equality of mixed partial derivatives. So if I have the second derivative of f with respect to y and x, that's equal to the second derivative of f with respect to x and y. It doesn't matter what order you take the derivatives in, as long as you take the appropriate number of the appropriate derivatives, you will get the same result. So let's do some examples here, clarify this out a little bit. All right, let's say we want d squared dx squared of sine 2xyz. Okay, so we're going to do partial derivative once. So partial derivative there is going to be 2yz cosine 2xyz. All right, and then for the cosine, that's going to give us a minus sign, so we're going to get the 2 from the interior again. We're going to get minus 4 y squared z squared sine 2xyz, if I can fit it in there. Yep, that says 2xyz, in case you cannot read my horrific handwriting. All right, so let's take a partial derivative with respect to z. Why not? Second partial, 4x cubed, y cubed, z cubed. All right, so that's going to equal the derivative of our first derivative, which will be derivative of z cubed is 3z squared. So that gives us a 12x cubed, y cubed, z squared. Derivative of that of z squared is 2z, gives us a 24x cubed, y cubed, z. Okay, so those are our standard second partial derivatives. We can do an example of a mixed partial. So let's say mixed partial derivative dx dy of, let's say, x squared natural log of y. So it's going to equal, we take the y derivative first. Derivative of natural log of y is 1 over y. So we have that. Derivative of x squared is 2x times 1 over y. So we have 2x over y. Now, just for fun, let's convince ourselves that this equality of mixed partial derivatives is true for this case. Let's do that in the reverse order. dy dx of x squared log y. Okay, so that is going to give us the derivative with respect to y. We take the x derivative first of 2x log y. Take the derivative with respect to y, log y is 1 over y, 2x over y. So indeed, it checks out for this case. You can convince yourself with many other cases that that will always be the case, that those two are equal. So that's the basics of repeated partial differentiation, same rules as you have for one-dimensional derivatives, except that we have the possibility of mixed partial derivatives coming into play.